Let's see how the models that we've been using for classification get extended to doing numerical prediction regression. So let's start out with nearest neighbors. And with nearest neighbors, the concept is pretty simple. Essentially, if you want to predict the Y value of a new individual, you dive into the training data, identify the K most similar individuals, and then just take the average value of Y to come up with your prediction. So what we do visually is this is our training data right here, two predictor variables x1 and x2. If we want to make a prediction on what this new individual's y value is, let's say right here, we dive in and find, say, the 5 nearest neighbors to that individual and just average together what those y values are. 8.7 in this case, 7.3 in this case, etc. So nearest neighbors extends pretty much the same as what you would expect, just in a regression context. The only question is, all right, what's the correct value of k to be averaging together? So if the value of k is chosen with cross-validation, once again, we don't know ahead of time if it's going to be best just to rely on just the single most closest person to that individual to make the prediction, or if we want to be averaging together a whole bunch of individuals. And then also, all right, what's the best way to measure the similarity between individuals? We're going to continue to use the default Euclidean distance, basically what a ruler would measure if we treated these individuals as locations on some sort of map. But the procedure extends as what you would expect, and it's very important to make sure that you're treating your data appropriately. One thing we don't know ahead of time is if we should be calculating the distances on the raw data values that have been collected, if we need to transform them to symmetry, if we need to scale them all so they have a mean of 0 and a standard deviation of 1. We don't know what's going to work ahead of time necessarily, so we very often fit the nearest neighbors models on 4 different versions of the training data to see what ends up working the best. Very often, the scaling plus transformation is going to give you the best model, but not always. It's definitely worth covering your bases. All right, how does the partition model in the vanilla partition model framework work? Well, it's going to work very similarly to when we did classification. We're going to start with all the individuals in one big mega partition, and then we're going to split that into 2 groups based on a very simple rule, like if a predictor variable is bigger than 5 or if it's less than 5. The only thing that really changes is exactly how we're adding rules to our model, how we're splitting up the partitions in half. Now, when we were doing classification, we were choosing rules to minimize the impurity of the resulting partitions. Basically, the 2 child partitions that resulted, we wanted them to have, all of one class and none of the other. Now, when we do vanilla partition models for regression, what we'd like to do is develop rules that make the 2 child partitions as uniform as possible. What I mean by that is that the y values in one partition should be all about the same. The y values in the other partition should be all about the same, or very different from partition to partition, but that's what we're going to end up doing. So same way we're going to make predictions presented with a tree model. We might want to classify, or not classify, make a numerical prediction for the birth weight of a baby born at 40 weeks to a smoker to a mother that was 5 feet tall. We start out at the top of the tree at the base node and we answer questions. If the answer is yes, we head off to the left. If the answer is no, we always head off towards the right. So is gestation less than 38? No, it's 40, so we head off to the right. Is gestation less than 40? Well, no, it's equal to 40 in this case. So we head off to the right once again. Is this mother a smoker now? And in this case, the answer is yes. So we head off to the left. And what we find is that the vanilla partition model has placed this baby in a partition with 112 other babies from the training data. The average birth weight of those babies was 3,420 grams. And so that's what's going to be our predicted value. All right, one thing that we really like about partition models is that they naturally incorporate interactions into the model itself. I just talked about how it's so difficult trying to get the right set of interactions into a linear regression model that very often we just throw up our hands and kind of give up. Now, partition models naturally incorporate them just based on the way that they kind of grow and add new rules to the model here. So one thing that we'll notice is that, say, smoking and gestation have an interaction. So how do I know this? Well, sometimes smoking matters and sometimes it doesn't. Notice when the gestation is less than 38 here, we can immediately make predictions about that baby's birth weight just on the value of the gestation alone. In other words, the value of smoking doesn't matter whatsoever. For larger values of gestation, though, we see that smoking does factor into it. So if gestation is bigger than 38, we end up somewhere over here. And in order to make a in order to make a prediction, we almost always have to use information about whether or not the mother is or isn't smoking. So the importance or the nature of that relationship between birth weight and smoking depends on gestation. We have an interaction. It's naturally been incorporated into the model itself. So a huge strength of that. Another huge strength is that unlike nearest neighbors, unlike regularized regression or linear regression, the vanilla form, we don't have to worry about transforming variables, and we don't have to worry about scaling the variables to have a mean of 0 and a standard deviation of 1. We get the exact same tree out with the raw data that if we had taken logarithms, or if we had scaled everything to have a mean of 0, a standard deviation of 1. We like models where the less things that we have to do with the data, the better, and tree-based models all have this property. Another huge, huge advantage. All right, let's revisit very quickly how we choose new rules to add to the tree. Remember, we add in one rule at a time. We start out with one big mega partition, then split it into two, then choose one of those child partitions, split it into two, choose one of the partitions that exist right now, split it into two. Keep going, keep going, keep going, keep adding new rules, keep growing the tree until we're done. How do we know what the best rule is to add to the tree? Well, it's going to be the one that makes the resulting child partitions the most uniform as possible. So what do I mean by that? Well, we're actually going to choose the rule so that the resulting sum of squared errors of the resulting partitions are as small as possible. Now, the sum of squared errors is, if we look at the child partition number 1 and sum up the square differences between the values of y we see in that partition and the overall average value of y in that partition, that's our sum of squared error contribution for that child. And same thing for the other child. Now notice, if we were able to discover a rule so that every single individual had the same value of y in that partition, well, the sum of squared error contribution of that would be 0 because everyone would have the average value. Ideally, we'd be able to come up with a set of rules so that everyone in a partition has the exact same value of y. Most of the time that's not going to be possible. We're just going to keep adding new rules so that we can basically minimize the sum of squared errors of the resulting child partitions, making the amount of uniformity in y values in those partitions as large as possible. All right, so some slides on how you go about choosing. We can look at that at a later time. What's our strategy for determining the number of splits? Well, that's tied into the complexity parameter of the tree. We don't just add in more and more and more and more rules. Sure, that's going to help fit our training data better. It's going to minimize the bias of the tree. But we know the generalization errors related to the bias and the variance of the model building procedure. The variance being a measure of how sensitive the model is to the particular set of individuals in the training data. It's sensitive to the complexity of the resulting model. So the complexity parameter basically tells us, all right, how much does the sum of squared errors have to decrease in order to justify the addition of a rule? And so the optimal value of CP is dataset dependent. We know we tune on it. We estimate the generalization errors as we vary the value of CP, and we choose the one that we think does the best. All right, so the vanilla partition model has a lot of pros. It's very fast to develop. It handles categorical variables without creating new indicator variables. Not very sensitive to outliers. They handle missing data easily. And they naturally incorporate complex interactions, and you don't have to transform or scale the variables. There's very little processing you have to do. It has a lot of advantages over, say, the linear regression. There are a few cons, though, is that even though we like a lot of their properties, they often don't predict as well as regression models. So that's a little bit too bad, but that's where random forests and boosted trees come in as an improvement here. So there are a few cons. So one con about it is that it is a high variance procedure. The entire tree structure can be sensitive to a single particular observation. So we know that the degree of sensitivity of the form of the model to the particular set of individuals is a measure for the variance of the model building procedure. The tree can completely change its shape depending on if you were to change, say, one individual's y value, if you were to bump it up or make it a little bit smaller. So because it can be so sensitive to that, we say it's a high variance procedure. Maybe one of the reasons why it doesn't generalize as well to new individuals. But that's where random forest comes in. That's where the idea of bagging, basically coming up with a bunch of trees and averaging together their predictions, It helps us to kind of compensate for an individual tree not being all that strong of a predictor. So with random forest, exact same thing we were doing with classification, except now we're predicting a numerical response. So we're basically creating an ensemble of individual vanilla partition models with a twist. So number one, bagging is employed. So each tree in the forest works with a slightly different set of individuals. They work with individuals in a bootstrap version of the training sample, basically picking individuals at random from the original data. Some might appear twice, some might not appear at all, so that you get to see slightly different sets of individuals each time you build a tree. And then more importantly, each time a new rule is to be added to the tree, a random subset of the predictor variables you have available to you are allowed to be the basis for that rule. So we don't exhaustively go through every single possible rule we could add to the tree to improve it. We just select, say, maybe 3 or 4 predictors at random and say, well, what's the best one of the rules from those predictors? We'll add that. And then we'll also actually grow the tree to the maximum possible extent. Each individual tree in the forest actually has each individual in its own node at the very end. But at the end of the day, once we average together all the predictions of each of the individuals' trees, it actually turns out we come up with a stronger estimate than just the vanilla partition model. In fact, the random forest model is the benchmark for most data mining competitions because it is so easy to use. Even this tuning parameter, mtry, the number of predictors you're choosing at random to base your new rule on, so when you're making a new rule for a tree, it's not all that sensitive to this tuning parameter, and so you can just pretty much go with the defaults. The number of predictors divided by 3 is the default here, and you come up with a pretty good model. So we can also get ideas of variable importance from the vanilla partition model and the random forest model. The variable importance on a random forest model looks at the total summa squared error decrease that variable was responsible for whenever it was used as a rule in any one of the trees in the forest. So it's kind of nice because when some of the strong predictors aren't selected to be rules on which we're adding to those trees, those variables that are weaker predictors, second place, third place, fourth place predictors, finally get a chance to shine because finally they'll actually get to be used as a rule for one of those new trees. So the numbers themselves, remember they don't tell us anything all that important, but the relative sizes do. All right, so pros and cons of random forest. It's almost all pros here. Very powerful, very flexible. It's the benchmark for data mining competitions. You don't have to scale your data. You don't have to transform your data. You only have to worry about potentially discretizing your data values if you have too many unique values in terms of levels of categorical variables or numerical values of a predictor here. But after discretization, you pretty much just throw the data at the random forest and it does a pretty good job at making predictions. So the cons is that, well, you can no longer really visualize the model. It's not like you can plot a random forest to make a prediction manually. And it does have a bias, like all of the tree-based models, of basing rules on predictor variables that have a lot of unique values. That's where that discretization scheme comes into play. All right, so what's better than random forests? Well, boosting is often a better alternative. However, boosting is very time-intensive for coming up with the right boosting procedure. So how does boosting work? Well, instead of building a whole bunch of trees and averaging together the predictions, boosting is going to build a sequence of trees, each building off the results of the trees that came before it. So the first tree in a boosted tree model is a very, very simple model with maybe only 1 or 2 rules that does its best at predicting numerical response. It makes a lot of error, and so the second tree comes along and says, all right, well, I'm going to try to predict the error made by the first tree. So it'll improve the predictions a little bit. Along comes the third tree. It tries to improve the errors that still exist after the first 2 trees have done their best, etc., etc., etc. So each of these trees in the sequence are kept very simple. The interaction depth of those trees is a number describing the number of splits here, and very often it's only 1, or maybe 2, or maybe 3 here. So the thing we have to worry about is tuning. Basically, how many trees do we need in our sequence? If we add too many trees, we can end up with an overfit model. Too many trees lead to basically modeling features that exist only on that set of individuals in the training data, so we have to be careful about that. We need to know how complex each tree is going to be, the interaction depth. We need to know what the shrinkage of the tree is going to be as well, the learning rate of the tree. So basically, small values of shrinkage correspond to low values of learning rate, And it turns out that slow learning trees that try to piece together the relationship one tiny bit at a time tend to be a little bit more effective and more powerful than trees that try to learn the whole relationship all at once. So what's the right value for this learning rate? And then when we're building these individual trees, what's the smallest number of individuals we're going to allow in any particular leaf here? So 4 parameters to tune, very time intensive, but very often we come up with an even more powerful model than the random forest model. We still get variable importances. We can still visualize what relationships look like as well. It's pretty neat stuff. This is really the state of the art. XGBoost takes this to the next level, where it actually employs regularization when coming up with these trees in the sequence. And so XGBoost is really the most powerful thing you can be doing in predictive analytics currently, but it is extraordinarily time consuming to tune the parameters there. All right, so that finishes off Unit 8 here with the predicting numerical responses with the models that we already know about. The next set of little mini lectures will talk about support vector machines, kind of a new and interesting way of approaching the problem, neural networks, and then also combining the results of all the models that we've talked about so far.